Okay, chapter 7, atomic structure and periodicity. In this chapter, we're going to we're going to learn how to extract the most information from that periodic table, because the periodic table is its design, its layout indicates atomic structure. You can infer atomic structure from that periodic table. And I'm going to show you how to do that. Okay, let's start off with how we know things. How do we know what we know about elements? Actually, how do we know what we know about the entire universe? Because that seems to be more significant, because we can't go out far enough to personally investigate the universe. As far as we've gone so far, just to the moon. That's it. The rest, we've sent out probes, and we've got a couple that are in interstellar space now, the Voyager 1 and 2. But when they communicate with us, when these probes go out and they investigate, they send us back information over the electromagnetic spectrum. And a lot of the investigations, the data that we obtain from far distances or from small things like atoms, we do it using electromagnetic radiation, light. So this fireworks display is supposed to show several different colors. I see some yellows, some oranges, some reds, some blues. There might be a green in there somewhere, except for the Capitol dome. But the question then arises, if this is how we get our information, why do we get these different colors? Why do we get different parts of the electromagnetic spectrum expressed to us as information from either far distance or very small stuff? And that's a fundamental question. Because we see these flame tests. If we put these different elements into a flame, they give off different colors. Right? So we want to know, why do they do that? And even further, not just flame tests, but why does something that we get a color from a flame test, but we put it in aqueous solution, we get an entirely different color? We see oxygenated blood, and the color there is is due to oxyhemoglobin. Right? You get bright red color from oxygenated hemoglobin, but when you take blood from a vein, it's a lot darker. Sometimes it even looks purple. It's got no oxygen in it, right? Because it's coming back to the lungs to get oxygen. So why the difference there between red and that? Of course, if you take your blood and you squirt it out on the table, right, it's going to turn red almost instantly because it's sucking oxygen from the air. Yeah, that changes the way. Now we know that oxygen, the transport mechanism in hemoglobin, is the iron in the center of the heme, the porphyrin ring, and the oxygen combines with that iron. And when it does that, it changes the absorption spectrum of iron. I used to work, in fact, I did my master's thesis on crawfish processing waste in Louisiana. There's a big industry. These companies would buy raw crawfish, live crawfish from farmers. Sometimes it'd come straight out of the bayou, right, wild caught, and sometimes it'd come out of rice fields. After a farmer cuts his rice, he refloods the field, and then the crawfish feed on what's left, the stubble. And sometimes he does it himself, sometimes he rents it out, and they put their traps out and they catch these farm-raised crawfish. But they are sold to these companies. Well, of course, there's a live market, but they're sold to these companies and they boil them. They have these banks of tables, mostly women, peeling them and putting the tails in bags, and they freeze them and send them all over the world. In fact, you can probably find them in the stores here, bags of crawfish tails. But that red color in the carapace of the crawfish is due to these carotenoid type pigments. And I got an example of one there. That's astaxanthin. And we want to know, why is it red and why is a different molecule that's similar to that, like beta carotene, why is it orange, right? In carrots, saying vitamin A is in that neighborhood. So why does it do that? Well, we don't have time to explain it now, but they're different colors, and it's due to the atomic and molecular structure. And we can trace it to transitions in the electron energies. The electrons move from different energies, and when they do, they either absorb or they emit light. So that's where we're headed. We need to characterize electromagnetic radiation so that we can use it. Light or electromagnetic radiation can be characterized with, can be quantified with these three values: wavelength, and we use the small lambda, Greek lambda, to be wavelength. And this wavelength is simply, we visualize light as a traveling wave, and the distance between two crests is the wavelength. And they can be very short, they can be very long, they can be miles long for some radio waves. Then there's frequency, right? That's the Greek letter nu. Sometimes some textbooks will just put an F in there for frequency rather than the Greek letter. So what do we mean by frequency? Frequency is as if you've got an eyeball and you're watching that wave past this particular point, and you count off 1 second. How many wavelengths past that point in 1 second? So it would be from here to, let's see, down, from here to here. That's your one wavelength. And how many of them pass that point in 1 second? So the values here, the SI units for wavelength would be meters. How long is that in meters? The frequency would be in how many cycles or how many wavelengths per second. Right? So that's the unit of measure there. Cycle, there's no unit of measure for cycles, right? Because it changes with wavelength. So it's just reciprocal seconds. But for some people that didn't sit quite right, and we wanted to give a scientist credit for his work. So they also call it hertz. But that's what it means, reciprocal seconds. And then we got the speed. How fast is that light beam traveling? And we give that a small c. Now this, for all intents and purposes, is a constant. There's a speed in a vacuum, and as it turns out, speed in air is pretty close. It's so close that you can't put a gnat's hair between them. And this value that we're going to use is 2.9979 times 10 to the 8th meters per second. So what does that mean? That means any one point on this light beam will travel 10 to the 8th meters in 1 second. That's fast. As my daddy used to say, lickety split. It would go, that's really fast. In fact, it's the speed limit for the universe. Okay, but all of these values are related, right? And they're related by this formula. Speed of light is equal to the wavelength times the frequency. So if we're going to consider this to be constant, then these variables are inversely proportional. As the wavelength gets shorter, the frequency gets higher. You get shorter wavelength, then in 1 second, more of them pass that point in 1 second. So with this being constant, if we know one of these, we can calculate the other one. Okay, and there's a representation. Now, the universe is more complex than that. This is our representation of a wavelength. In fact, electromagnetic means that there's an electrical component and there's a magnetic component to a light beam. And they usually represent them as right angles to one another. So you get the electrical component doing this and the magnetic component. Okay, here's the electromagnetic spectrum. And I always chuckle when I see science fiction movies or television shows. And they mention different types of radiation. Now, radiation is the sky's the limit. But if they're electromagnetic radiation, that's it. That's all there is. And we get this continuum of electromagnetic radiation and be consistent with what they've got there. This would be the wavelength, and the longest ones would be down here. Shortest wavelengths will be down here. As it turns out, the visible part of the electromagnetic spectrum, the part that we can see, is just a small sliver of what constitutes the universe. And that's why it was blown up like this, so you could see individuals. So the longest wavelength is going to be the red end. The shortest wavelength is going to be the violet end. And I don't know in grade school if you learned the colors of the rainbow. Roy G. Biv. So it's red, orange, yellow, green, blue, and I'm not so sure about this one, indigo. And I saw indigo as another shade of violet. That's what we can see. And it runs from about, let's see, about 400 nanometers, and I'll explain that in a minute, to about 700 nanometers. A nanometer, a nano is 10 to the minus ninth. So the wavelength here is 400. We could say 400 times 10 to the minus ninth meters. Right? So it's really a short wavelength that we can see. Okay, on this end of the spectrum, anything longer is called infrared. IR, infrared. And that's generally considered to be heat. Right? Those are the types of lamps that they put over your food in a restaurant to keep it warm until it's served, infrared lamps. Then the next longest ones will be microwaves. And yes, those are the same microwaves. One part of that is what heats your food. Okay, so we got up to microwave is a longer wavelength than infrared. And then this wide band where we have radio waves. And this can be subdivided into, FM is the shortest one. And then we get shortwave. So this is where the ham operators live. And then AM is probably the longest. And we won't talk about what those mean right now because that's not relevant to our discussion. This end, where the wavelengths get shorter, violet, ultraviolet is in here. Right? You have different bands of ultraviolet. Some are more hazardous than others. Okay. Then you get a section in here for X-rays. And we all know X-rays, right? They just blast your body with X-rays and then they get a picture. Right? It's not as hazardous as it used to be because they don't use film anymore. They use more sensitive electronic detectors. So they don't have to hit you with as much X-ray to get a picture. And then the shortest wavelengths are the gamma rays. And let's see, gamma is that Greek letter. These are the shortest wavelengths. And we're going to find out very soon that, let's see, longer this way, shorter this way. And since they're inversely proportional, then the frequency or the frequency is shorter this way. I should say smaller. Shorter implies length. Smaller means you have fewer wavelengths passing a point at any one time. And this way it's larger. So you have more wavelengths passing a point at any one time. And also, the frequency is proportional to energy. We can also say this is smaller energy with frequency. And this is larger energy. So what that means is these X-rays out here are I left out gamma. That's X-ray, this is gamma. And I can't even read my own Greek writing. Huh? Gamma rays, the very shortest wavelengths here are gamma rays, and they've been discovered. We can create them ourselves, but in nature, you see them coming from distant galaxies and exploding stars and things like that. These phenomena that are detected in the universe can produce very energetic gamma rays, very high energy. Fortunately, the higher the energy, the more directional. So when these beams are produced, you can see some scatters off the side. That's how we detect them. But if we're ever in the direct path of a gamma ray burst, it's going to be curtains for this Earth, because it will strip the Earth of its atmosphere in just one burst. So that's how dangerous they are. Fortunately, the odds of ever encountering that are almost zero. Fortunately, yeah, for us. Okay, so that's the electromagnetic spectrum. Let's see. Okay, that's enough said about that slide. Yeah.
On the chart, it's you've got on your board in the chart.
Mhm.
Do we go by the 400 10 to times 10 to the minus 10, but on the chart it says 4 times 10 to the minus
Okay.
7.
That's meters also.
Okay.
If we take this and take those two, 100, that decreases this to -7. So they're the same.
Okay.
They're the same numbers. The illustration here is that 10 to the -9 is the nano part.
Okay.
That's why I left the 400 by itself.
All right.
So this is in meters. And sometimes when you do calculations, you need the meters. And in fact, most of the times you need the meters. But for convenience, sometimes we use nanometers, 400 nanometers to 700 nanometers. So you'll see it both ways. Okay. This is an illustration of the equivalence of energy and light. So we put a direct current through this pickle, and it's going to conduct electricity because there's vinegar in there. It's ionized, so it'll transmit a current. But there's a lot of resistance. So that resistance robs the current of energy, and the energy's got to go somewhere because you can't create or destroy energy. It's got to be converted. So it's converted into light. So that's why the pickle glows yellow. I don't think I want to eat it after that, though. Okay, this is a little history lesson. In the late 19th century, scientists were trying to figure out what's the nature of light. And James Clerk Maxwell was he was a polymath. He had his fingers in lots of pies, but he was a mathematical genius. And he developed a series of equations that completely described the wave nature of light, electromagnetic radiation. So the first winner in this project was wave nature of light. We're going to find out that it's not as simple as that. But when we talk about light in terms of waves, those equations still work just fine. And they also agree with general relativity and quantum mechanics. So general relativity is things that are huge, lots of gravity, massive, and quantum mechanics is everything that's too small to see. Unfortunately, scientists at the dawn of the 20th century said, we got an easy job from here on out, right? We've described nature completely, and all we have to do now is tweaks, refinements. We don't need to know anything more fundamental about nature, and they couldn't be more wrong. Because it's the something inside scientists that tells them that there's got to be more. Right? And there are always young, hungry scientists coming up that are going to push the boundaries. And one of those scientists happened to be Albert Einstein, among others. One of those others was Max Planck. Planck, I think, was German. And he was particularly interested in what was called black body radiation. That simply means that the object, whether it's this small or it's as big as a star, was not considered an energy producer of its own, a light producer. But if you heated it up, as you heat it up, more energy is emitted as radiation. You could detect radio waves as you heated it up, and then higher temperatures mean microwaves. Then you could get in the visible range. And if you got hot enough, you could get into these shorter wavelengths. So the temperature and the energy of the light coming from that object were correlated. But it was assumed that the body itself didn't produce any energy of its own. It was completely related to the temperature. Now, we know that's not true, but it was a good way to assess the temperatures of, say, stars, if you could detect their colors. Like blue stars are hotter than yellow stars. And red giants, like we find one, the most prominent one, I think, is in the constellation of Orion. I can't remember the name of it. Betelgeuse, maybe. I think it's Betelgeuse. Not the actor. But it's a cooler star because it has a redder color. But he was interested in this correlation between energy and light. And it eventually led him to this equation where he said the energy of light coming from this black body is proportional to, let's write it that way first, is proportional to the frequency of light. So as the frequency goes up, the energy goes up. Frequency gets larger this way, you got more energy. But the units didn't. This is in joules, and this was in hertz. So what you need are reciprocal seconds. What you need is a conversion factor. So in order to make them equal, he had to find a conversion factor that would convert the units of this into the units of that. And this is called Planck's constant. That H. And that's usually what these types of conversion factors are good for. They're just converting units. You know that there's an equivalence there, but you can't say it's equivalent until you get the units to jive. So, in addition to this relationship, we normally think of energy as being not contained in waves, but contained in particles, in objects. So this was the first indication that light may also be considered as a particle. And Planck called it a photon. Right? So the next logical step is to make photon torpedoes and put them in a television show. Star Trek. It was only on for just a few years. And then the franchise just exploded into movies. Anyway, so these packets are quanta of light. So whenever you see quanta, think packet of something. In this case, quanta of light is a photon. And there's the relationship. Okay. Now, we can take this equation and do some fancy math. We've seen this equation already, right? Where you have wavelength times frequency. Well, if we solve this for frequency, then we get speed of light over wavelength, right? Just take this over here. Now, if we substitute that in here, we can also, we have a relationship between energy and wavelength that we can use. So this would be C over like that. So if you're given a wavelength and you need no energy, you don't have to convert it into frequency and then put it in the equation. You can just use that equation and do it all at once. There's Planck's constant. Sometimes I can remember it and sometimes I can't. 6.626 times 10 to the minus 34, I think. 34 joule seconds. If we do a little dimensional analysis, if we put joule seconds in here, times reciprocal seconds, which is 1 over seconds, then the seconds cancel, leaves us with joules. So we're good. That's Planck's constant. Oh, I got a video coming up.
Everybody knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also— What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect. Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is, what if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions. So he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
Okay. So Millikan, and we saw him before, he was the one that measured the mass of an electron. They each won Nobel Prizes. Einstein won his in 1921 for his work on theoretically describing the photoelectric effect. And then Millikan followed up 2 years later in terms of the Nobel Prize by physically verifying it. Einstein at the time, he came up with this photoelectric effect and published it in 1905. He was a patent clerk in the Swiss patent office in Bern, Switzerland. And he'd have so many patents he'd have to review in a day. And he'd get them all done in a couple hours at the beginning of the day and spend the rest of the day at his desk thinking about this stuff and working on it on paper. So now we have this controversy. Is light a wavelength? Is it a wave or is it a particle? And Einstein put them both together in this concept of the photon, where you have the wave nature in packets. Now, the reason that he had to do that was, as described in the video, the photoelectric effect would only work for light of a certain energy, usually from here down. Had to have enough energy. And the photoelectric effect is simply, if you shine light on metal, usually it's metal, and you shine light, then as you decrease the wavelength and increase its energy, eventually you reach the point where there's enough energy to eject electrons. And there's one particular, for every metal, there's one particular wavelength where it starts to eject electrons. And below that, the energy is sufficient to eject electrons all the way down to however energetic you want. But the minimum amount of energy that's required, the threshold frequency, will simply remove that electron to its minimum position of infinity above the atom, where it's not connected to the atom anymore, but it's just sort of sitting there. If you increase the energy beyond, if energy is greater than the threshold energy, then the excess energy is converted into kinetic energy. And those electrons now have some velocity. And the shorter you get the wavelength, the more velocity they have. So the energy is not wasted. But Einstein had to approach this in a different way, because if the wave theory only was responsible for the nature of light, then any one of those wavelengths should work. It just, all you have to do is increase the intensity, make more of these beams hit that spot. And eventually you would cause the electrons to vibrate enough to where they jump off the atom. But it doesn't work that way. So Einstein had to come up with a modification. Okay. So anything above here, increasing intensity doesn't do any bit, doesn't do a bit of good, right? But increasing intensity, once you start to get electrons released, increasing intensity simply makes more electrons leave the surface. Okay. So we got these photon packets with a required minimum amount of energy. Let's see. Let me get this out of my way. I can't do it. There it goes. Oops. Let's go back. So the photons that possess less than the required energy, if they dump their energy into this metal, then it has to go somewhere. It's not going to go into ejecting electrons, so it must be converted into something else, and it's usually heat. That's why they call them thermal photons, because they're not photoelectric photons anymore. And I mentioned that already. You get kinetic energy if you have higher energy than is required, and the intensity simply makes more photons leave the surface. So, what does this photoelectric effect tell us about the structure of the atom? That's where we've been headed all along. Well, if light arrives as a photon packet, it has a certain amount of energy with a photon. Then what we see is, well, that there's an interaction between this photon of light and the electrons in an atom. I mean, that's obvious. And when that happens, the absorption of this photon of light is by means of the absorption of that energy into the electrons of the atom. So that tells us that there's a structure in there to the atom with respect to those electrons. And what science eventually came up with is you have this nucleus. Of course, it has a certain number of protons and maybe some neutrons. And then you have electrons out here at different levels. And say you have an electron here, say it's hydrogen, you only got that one electron. And you hit it with a photon of light that has sufficient energy so that it is now absorbs that energy. Where is it going to go? Well, as it turns out, the energy of an electron is based upon its distance from the nucleus. All right, so if this absorbs some energy, it may be promoted to the next level. And as it turns out, the energy is quantized. If that photon is not the right amount of energy, then that electron won't move. That's got to be exactly the right amount of energy to make it go from here to here. Or if it's more energy, it may go from there to there, or it may go from there to there, or it may go to infinity. It might leave the atom. That's the photoelectric effect. So that gives us some idea that there are levels of energy for the electrons surrounding the atom. Okay, let's see. Oh, by the way, if these electrons have, or photons have kinetic energy, if we can measure a kinetic energy from the photon, then that's another indicator that photons can have mass also. Right, so where am I headed with that? Well, eventually we circle back, as they say, circle back to Einstein. You get a universe that has mass also can be converted into energy. Or if it's energy, it can be converted into mass. They're interchangeable. Right? It may take special conditions to do it. Like, so for instance, an atomic weapon would take part of the mass of your uranium-235 and convert that mass into energy. And since this is light, the speed of light squared, just a little bit of mass gives you a massive amount of energy. Okay, there's my favorite picture of Albert Einstein in his golden years. That's, when you get old like that, and you've already made a name for yourself, you can be as silly as you want. Other pictures, you see him riding the bicycle backwards. He's sitting on the handlebars. Okay, so in 1905, Einstein also produced his special theory of relativity. So he did the photoelectric effect, then he did special theory of relativity. And this is where he equated light energy with mass. Now there's a difference here. This is not rest mass, this is relativistic mass. Relativistic means very close to the speed of light. Okay. And we could jump on that horse and ride off in a different direction if we wanted to, but there's no time for that. So he came up with this equation in his theory of special relativity. And then in 22, a couple of decades later, Arthur Compton actually confirmed experimentally this relationship. And I think he got a Nobel for his confirmation. So you get the theory first, and then you get the physical confirmation, and they both get Nobels. So we have this dual nature of light. It's both a particle and a wave. And the way you treat it as either a particle or a wave depends on the phenomenon, right? And we're going to look at that in just a minute. What phenomenon indicates which nature? Photoelectric effect is primarily particulate nature, but it also carries with it the wave nature. So photoelectric effect is sort of a hybrid of both the particle and the wave. But sometimes you get phenomena that are easily separated. They're both correct, actually. Now, this phenomenon called diffraction, where in the way it's illustrated here is you've got this wave of light that strikes a barrier and there's a pinhole in the middle. That pinhole serves as a point source for a new wave. That's why you see it propagating out from that point. That's called diffraction. Another way to look at it is if you have a barrier here and you have this light strikes the barrier, if light were a particle, then it would do like this, right? And on your detector over here, it would just make a bright spot right there. But it doesn't do that. It makes a fairly intense spot here, but it decreases in intensity as you go out. So that means that at this corner, right, it's acting like a wave, and it gets less intense down here and it's more intense there. That's diffraction. I like to think of it as light turning a corner. Refraction is also attributable to the wave nature of light. Refraction is like lenses. So when light travels through a lens, let's make it a flat surface. It's easier to describe. The wave is approaching this lens, and when it does, the speed of light is not constant for every material. So in these more dense materials like polycarbonate or flint or crown glass or whatever the case may be, when they strike that material, light does interact with matter. And when it does, it slows down. So this part of the wave slows down, and then the next wave hits it, and it slows, let's see, it slows down some more. And you eventually, if you say the direction of the wave is this way outside, then the direction changes when it strikes that material. That's refraction. Now, if you make it a lens, right, you can cause the light to do certain things and make it bend en masse and hit a point down here and focus. Right. So that's what lenses are made to do. But you can use just a straight sheet of glass and see the effect. But the particle nature of light is primarily photoelectric effect, even though that this photon of light carries within it the wave nature. Now, how does that relate to the light that comes from different elements, the different colors that come from elements? Well, the best approach to this is the simplest approach. Use hydrogen, because it only has one electron and one proton. Simpler is better when you first start looking at these things. So we observe in nature, we can draw a line between two types of spectra. Continuous spectra, where you essentially get every wavelength in the spectrum, or at least in the visible part of the spectrum, you get every wavelength. And we see that from the sun. We can get light from the sun, and if you put a prism out here, you can see all the colors of the rainbow. But if you have trapped in a discharge tube an element like hydrogen, and you spark it with some electrical energy, and that converts into light, then what you get from hydrogen is a line spectrum. Right? In the visible range, you only get 4 wavelengths, 4 colors. Okay, so that's part of our investigation. That answering that question tells us a fundamental truth about the atom itself, is the line spectrum. So that's one of my favorite pictures. That's from my Pink Floyd album. That's the only album I ever bought, Dark Side of the Moon. That was back when you had vinyl. That was the only album I ever wore out and had to buy another copy.
The discharge tube is filled with hydrogen gas. When a high-voltage electrical discharge energizes the gaseous atoms, light is emitted only at specific wavelengths. The emission spectra obtained are called line spectra, due to the appearance of bright lines. In the hydrogen emission spectrum, there are 4 lines in the visible region. A purple line at a wavelength of 411 nanometers, a dark blue line at a wavelength of 434 nanometers, a green line at a wavelength of 486 nanometers, and an orange-red line at a wavelength of 656 nanometers. Let's look at the electronic transitions responsible for the observed line spectra. When an electron drops from a higher energy orbit to a lower energy orbit, a quantum of energy, a photon, is given off in the form of light. During the electronic transitions shown, light is emitted in the visible region of the electromagnetic spectrum. You may click on the buttons to review each of the electronic transitions individually.
Okay, so there's a representation of those energy levels I drew for you around the atom. And notice that for the visible spectrum, the electron jumped from N3 to N2. That was the shortest distance, which means the lowest energy. And that would be this one right here. And then we went from 4 to 2 and 5 to 2 and 6 to 2 gave you more and more energy because the jump was bigger. Now, the reason we didn't jump from any of those down to 1 is if it jumped to 1, there'd be so much energy, couldn't see it, right? It's in the ultraviolet region. And there is a spectrum in the ultraviolet region. Right? They have series names for them. I think this series name is called, well, I don't want to say, because I'm just trying to remember and I can't verify it, but they had names. And these are the visible ones. This tells us that the movement of electrons around the atom is also quantized. It only happens in discrete jumps. Only certain energies are allowed for the electron in the hydrogen atom, but we find that later that this discrete jumps also are valid for every other element in the periodic table. It's just with more electrons, it becomes more complex. Okay. So to answer the question, why is the light not white? It's because you don't have all wavelengths of the electromagnetic spectrum. You only produce white light when you've got a combination of wavelengths that cover the entire spectrum, and then we perceive them as white. Right? That's another thing that we've sort of sidestepped in this explanation, is that when we're looking at colors, there's also physiology involved, and we're trying to stay pure chemistry. It's hard to do because we're using our senses. Okay. So I'm going to say this several times during the discussion. And this is that we can't see those electrons move. We deduce that their movement is quantized by this evidence. But there is always a slight probability that the electron, rather than ending up right there, might be there or it might be there. So when we talk about things at this level, I may have mentioned this before, at this level where we can't see, we talk about these things in terms of probability. The highest probability is that electron will be at that energy or this energy or this energy, depending on its intrinsic energy value. But there's always a probability that it may blur some. And then we say the probability that an electron will be in this region is 0. Okay, I just wanted to make that distinction for now. Okay, so along comes a Danish physicist, chemist. Name was Niels Bohr. And I think he spells his name like this. Niels Bohr. I think I before E, even in Danish. And he was modeling the atom after the solar system. He was saying, like the sun, the nucleus is in the center, right? And he restricted his model to the hydrogen atom because that's the only one he could get to work with his model. So we've got one proton here. And then we've got an electron out here at this energy level. That's called the ground state. The ground state for hydrogen is the first energy level for the electron. Ground state for other elements might be further out because these levels are already filled with other electrons. So the ground state will have everybody at the lowest possible energy. And closer to the nucleus is lower energy. Okay. So in setting up his model, this is not to scale because the jump between 1 and 2 should be a lot bigger than that. In fact, let's do it this way. There's 2. And there's 3. And then 4 is even closer. And then 5 is even closer than that. Okay. So this is Niels Bohr's planetary model, so to speak. And we've seen that before, that model. They did leave out one wavelength, though. The jump from 6 to 2 would leave out the shortest of the wavelengths here. Yeah, what's missing? The fourth emission line. This is another way to represent it. Now, in this case, they're not showing the nucleus. That inner circle is actually the n equals 1. This is also known as the principal quantum number. Okay. Niels Bohr came up with that one. And in future models, we hold on to this one and add to it. Okay, so when you jump from 6 to 2, you get 410 or 411 nanometers is the emission. So anytime you go from high to low, you shoot out a photon of light. Anytime you go from low to high, it has to receive the correct amount of energy to go from this level to that level or this one to this one. It has to be exactly the right wavelength. So how do we calculate the energy of an electron for an energy level? Well, there's this equation which Bohr proposed and others refined. And that first number there, that minus 2.178 times 10 to the minus 18th joules, is a conversion factor. Because Z, remember, Z is the same as we've learned before. That's the number of protons, right? That's the atomic number. And N equals the energy level, the principal quantum number, principal quantum number. So if we want to calculate the energy of any electron in this model, we can say this electron has a certain energy. We would put 1 in for the Z and 1 in for the N. And so times that, and its energy level would be minus 2.178 times 10 to the minus 18 joules for an electron right here. Okay. If we want to calculate, say, for this electron, we would put a 2 in there for N. So that would make it a half of, so it'd be 1.89. Minus 1.89 times 10 to the minus 18 joules is the energy here. Now, why are they minus? Because more minus is lower energy. So as you get closer, you get more minus. And you're going to get the small, lesser and lesser minus as you go out until you reach infinity, where the energy is 0 relative to the nucleus. And that's considered a position of infinity. Okay. Okay, let's see. So if you want to calculate the energy that is emitted when you jump from a high to a low, or the energy that is absorbed when it goes from a low to a high, you have to subtract one from the other. The energy at this position minus the energy at that position will give us the amount of energy emitted. Okay, And whether it's positive or negative really doesn't matter. You would take the absolute value of it and use that energy in Planck's equation. Right? You would take that energy and this constant and calculate the frequency of that light. You could do that. And the observed frequencies of light relative to the transition of the electrons matches perfectly. So here we've condensed it. We've done a little math there. We extracted that constant, pulled it outside. And of course, for a hydrogen atom, the bottom equation is the one you would use because Z equals 1. Now you can do this. You can use this equation for non-hydrogen atoms, but in order to do that, you have to have ions. You've got to have only one electron. You can use different values for Z, right? But that only works if, say, if we used helium, it would have to be helium plus 1. That leaves us 1 electron. Or if we used lithium, it'd be lithium plus 2 or beryllium plus 3. You can only have 1 electron in order for this to work. But you can have any number of protons. Okay, so for the hydrogen atom, transition from N5 to N2 is blue light, 434 nanometers. If we used our formula, right, and we put the values in there, final is 2, so it's going from 5 to 2. Final is 5 to 2. 2 is first and 5 is second. We calculate that the energy change would be that many joules. Okay. And then if we take the wavelength and use that modified equation where we have wavelength and speed of light and use Planck's equation, we calculate that the value of that energy of that photon of light is almost exactly the same. So that's just confirmation that one supports the other. Okay, so this quantized model for the hydrogen atom was our first step toward understanding the structure of the atom. I mean, in terms that we haven't looked at before. I mean, early on we looked at, all right, the atom's made up of protons, maybe some neutrons and electrons, and that's where we left it. But now we're looking at the structure of the atom with those parts in place. Now, of course, we're not going to go into the nucleus, right? That's nuclear chemistry or physics. We don't have time for that. Okay. The fact of the matter is, and this nearly always happens, the Bohr model is incorrect. For one reason, it only works for hydrogen or hydrogen analogs, where you only have 1 electron. Okay. It also assumes that electrons move around the nucleus in circular orbits. They stay at these distances, but this particle, this electron is going around like that. Well, let's see. If we're looking at from above, it should be going that way. Right? We don't have any retrograde planets in this solar system. We got some retrograde moons, but no retrograde planets. But that's not how the electrons behave. They don't move in circular orbits like that. The reason that we know they don't do that is, by analogy, we know that satellites that are in circular orbits, eventually their orbits decay. And the gravity pulls them in. And then once they get close enough to the atmosphere, then their orbits start to degrade. And if this model were true as circular orbits, then eventually all those electrons come crashing into the nucleus. But they don't do that. Good, thank goodness. All right. So those are the transitions and those are the lights, and that's the exercise. Okay, we're going to digress for just a minute. And the reason we need to digress is to emphasize the point. And I guess you call it, the point is uncertainty. Werner Heisenberg was a German chemist, physicist. And his work allowed him to propose this equation. In fact, the real equation is more complex than that. This is a simplified version for our benefit. But it draws a comparison between the position of any object in space or around an atom, doesn't matter, and its momentum. So mass times velocity in physics is called momentum. Well, for any given particle, the mass is constant. So we're really looking at a change in velocity. And change in velocity means energy. Okay, so what we're looking at is position versus energy. All right, what he said was that there is uncertainty in the particle's position. That's delta x. That's the amount. So if delta x is huge, then we essentially don't know where it is. And if mass times velocity, that is huge, then we don't know what its energy is. But we may be able to determine where it is. So as the particles get smaller and smaller and smaller, these values become more significant. And when you multiply the change in position times the change in momentum, it's always got to be greater than or equal to Planck's constant divided by 4 pi. Okay. So what we're, to wrap this up in a neat package, at this level, when we're looking at small things like electrons, even atoms, we can do two types of measurements. We can measure their energy or their speed or their momentum, whichever the case may be. But if we do that and we get that fairly accurately, we don't know where they are. That seems counterintuitive, right? Well, it is at this scale. But on that scale, it's a fact. But if you want to know exactly where it is, you can't tell how fast it's moving. That's the gist of the Heisenberg uncertainty principle. Now, there were a lot of other people working in this area. Max Planck's listed there, Albert Einstein, Louis de Broglie was a French genius, and we'll talk about him again later. There's Erwin Schrödinger. You ever heard about Schrödinger's cat? No. It's kind of gruesome, but it's just a thought experiment. We don't have time to talk about it right now. Max Born was another. Paul Dirac, he was I don't know if there's a word above genius, because he was there. Pauli, we'll see Pauli again, and there were others. So when we talk about probabilities, so that's what we do with electrons. We're more interested in their energies than we are in their positions. So instead of saying this is where exactly the electron is located, we say it's more important to know what its energy is, at which level. And we describe the position in terms of probabilities. And that this probability function has this term in it, and that's the Greek letter psi. If you've ever seen fraternities, a lot of them have that symbol in their 3-letter names. But psi squared is a part of that function, tells you the probability of finding an electron near any point in space. So it's still probabilistic. And what computers tend to do now is draw us a scatter diagram. And they say around this nucleus, if you've got certain energy for your electron at this level, according to the Bohr model, well, the psi function is going to say, okay, it's distributed kind of like that. So it'll give you a distribution. This is where you're probably going to find it. So that's what psi squared means. And when we try to represent these, what we call electron clouds, we can do it in a number of different ways. We can use that blue cloud up there for the number 1, and it tends to be dense down close to the nucleus. It doesn't show the nucleus, it's in there. It tends to be closer to the nucleus, and then you get probabilities out here for location. But still the energy is known fairly accurately. But the position is kind of fuzzy. This is another way to represent it. The distance from the nucleus. Notice the distance from the nucleus at 0. The probability of finding that thing there should be 0. You don't want your electron at the nucleus, right? That would quench the protons and no more atom. But its highest probability of finding the electron is at that distance, that hump. That's the highest probability of finding the electron at that distance. These are three-dimensional electron density maps, are difficult to show in a two-dimensional screen. And we generally work, does anybody have statistics in here? Okay. If you do take it, then you'll be introduced to this probability thing and the confidence level. In this case, when we draw this three-dimensional electron density map, we're 90% confident that the electron's somewhere in that region. Okay. In statistics, we usually go a little higher, 95% confidence level. So there's, on the flip side, there's a 5% chance that we're in error. Okay, now for our quantum numbers. When we talk about quantum mechanics, we're talking about a system of equations that tell us, that give us the probability of finding an electron at a given energy. And these equations come with 4 numbers, these quantum numbers. And you plug those numbers into these equations, and it spits out this density. And the reason we're spending so much time on these is because these quantum numbers tell us how that table is arranged. Okay, so we've talked about the first one already. That's the principal quantum number. And it's just 1, 2, 3, 4. It's digital. It's whole numbers 1 through whatever, up to any number. So this principal quantum number, probably should have left it up here. Principal quantum number can be 1, 2, 3, 4, up to however many. And what it tells us in those equations is the relative size and energy of this orbital. The orbital is another word for this is where the electrons probably stays. So this was related to size and energy. They go together because the size of the orbital, if it's bigger, then the electron is further from the nucleus and it has lower energy. So they go together. The next number is the angular momentum. Quantum number. And think of these as a branching tree, right? So any one of these quantum numbers we can take it and derive the angular momentum numbers for that particular principal quantum number. So this one will have a set, this one will have a set, this one will have a set. And we take the principal quantum number, we start from 0, and we go up to n minus 1. So the highest level you can get for 4 would be 3. The highest level you can get for 2 would be 1. And the highest level you can get from 1 is just 0. Okay? So it branches. And we go down here and we branch again and branch again. And that's the pattern. Each time you go to another level, you take one of these and it branches. And the angular momentum quantum number tells us something about the shape of the orbital. So it could be spherical. It could be dumbbell shaped. Dumbbell shaped. Or it could be a toroid. Could be like that. Different shapes. And these representations, if you see graphs of these, that's what we think it looks like. We've never seen it. The equations tell us what that shape is. But since we've never seen it, lost my train of thought. Let's see. We may not have seen it, but the physical and chemical behavior of the elements, once we describe them this way, matches with our descriptive terms. Okay, so there's evidence that what we're doing with these quantum numbers and the equations that follow is they're true, they're accurate. There has to be some evidence for it, and we do see that. Your book may call this this is sometimes called a shell. This would be a subshell. Right. Just in case you run across those terms. And then the level below that is magnetic quantum number. Okay. And it takes any one of these and it goes from, oh, and by the way, this is, let me fill in the letters that these were, this is N, this is L as the symbol. This one is M sub L. And it's derived from any one of these. And you say it goes from minus L up to plus L in digital increments. Right? It goes through 0 by ones. So for this one, it would be -2, -1, 0, +1, and +2 are the possible magnetic quantum numbers at that level. If we went to this level, it'd be -1, 0, +1. That's it. And this level would just be 0. And the last one, which is actually the easiest one, is the spin quantum number. Oh, what does the magnetic quantum number mean? It's spatial orientation. So I like to think of it, if we describe the shape as a dumbbell, right, looks like this, it either points this way or that way or this way, or maybe off that way. Its spatial orientation tells us something about that. The spin quantum number is just that. It's electron spin. Electron spin quantum, and its symbol is M sub S. And this one can only be +1/2 or -1/2. It doesn't matter what these are, that's all that it can be. Okay, those are your 4 quantum numbers. This table illustrates what you can expect from n equals 1. N equals 1, L can only be 0 because it has to be n minus 1. And M sub L can also only be 0 because minus 0 is 0, plus 0 is 0. That's it. And then for each, if you go from 1, 0, 0, then you can have plus half minus a half. So the number of, let's see, this is shell, subshell, orbital. The M sub L is called an orbital. And the number of orbitals, if n equals 1, you've only got 1 orbital. If n equals 2, right? If we say n equals 2, then you could have 0 or 1, right? And the 0 could only have this one and this one. So the 0 implies only 1 orbital. But 2 implies 0 and 1 at the 2 level. So we've got n equals 2. Let's see. Excuse me. If this is n equals 1, then n equals 2 can give you either 0 or 1, and then the 0 can give you another 0, but the 1 can give you minus 1, 0, or plus 1. So at this level, you can have 4 orbitals. You can have, there you have 1 plus 3. That's 4. Okay. All right, so it just expands, it balloons. So if you look at the periodic table, you see that as you add levels, and you always add them at the lowest energy, and they start building out as you go from one element to the next one. Add more protons, add more electrons. Notice that at the top of the table, right, you've only got hydrogen and helium. And in the next level, you've got lithium through neon, sodium through argon. And then you start getting more and more as we stack up until you get down to here. All of these go right in there. All of these go right in there. So it shows you that branching, it just expands. Okay, so let's take this example. Let me erase this. It's confusing. For principal quantum number 3, well, that's 1 and this is 2. 1 and 2. So principal quantum number 3, determine the number of allowed subshells. How many subshells can you have from 3? Well, you can have 0, 1, 2, and 3. It's just 4. You can have 4 subshells if n equals, oh, excuse me, 0, 1, and 2. 3, 0, 1, and 2. So if you have 3, you can have those 3 subshells. There we go. I got to get back in the group. Okay, let's see. Oh, and while we're here, I'm going to add this. When we write out the electronic configurations of an atom, and we say, this is where the energies, this is where the electrons are likely to be in these orbitals. If we use numbers only, we say 3, 2, it gets pretty confusing. So instead, we assign letters. So the 0, L is an S, 1 is a P, 2 is a D. Somebody's trying to call me. And if we have a 3 here, it would be F. And that's as far as we need to go to cover all the elements in the periodic table. SPDF. So that's why when we say if L equals 0 at this level, it's 3S. And for L equals 1, it's 3P, 3D for L equals 2. No. There we go. Okay, let's see. For L equals 2, determine the magnetic quantum numbers. And the number of orbitals. Okay, so if L equals 2, it doesn't matter which one it could only come from this one. It has to be 3 or higher in order to get L equals 2. But if we have L equals 2, well, let's see. That would be D. So where can we go from there? Well, D would be -2 for the magnetic quantum numbers, -1, 0, +1, +2. So you can have 5 magnetic quantum numbers at that, or 5 orbitals for L equals 2. Okay. There we go. Now, here are different ways of representing those orbitals. For the 1s orbitals, we find that we have a probability that's very close, that's highest, closest to the nucleus. Now, this is a little misleading because as you get close to the nucleus, the probability drops to 0. So they left out that part of the graph. But this is a comparison of s orbitals, or the 0 L number, for 1s, 2s, and 3s. So you can have an S from here, you can have an S from there, you can have an S from there. And when you look at those, they're all spherical, right? That's the shape. S orbitals are all spherical. But the density is not continuous out to its limit. What we find is for the 1s, it is continuous. Once you get some density, then it's continuous to its limit. But for the 2s, you have one node in there. See where it dips down to 0 and then comes back up? That when it dips to 0, that's called a node. We're saying that there's no probability that we calculated for electrons to be in that region. Okay. And when we get to 3s, we get 2 nodes for the s orbital. For the p orbitals, the p orbital shape is 1, and they're this dumbbell shape. And there are only 3 of them, right? P can be -1, 0, +1. This one would be aligned, say, with the x-axis. This would be aligned with the y-axis, and that would be aligned with the z-axis. That's what it looks like. Now, I emphasize again, we've never actually seen those, right? This is calculated. This is artist rendition. Now, when you get to d orbitals, some of them are dumbbells, and one of them has a toroid in it. So it gets really complicated in a hurry. But you can have 5 of them, like we calculated before. -2, -1, 0, +1, +2. If you get to 3, now you've got -3, -2, -1, 0, +1, +2, +3. And that looks really wild. And that's calculated from those equations. It's that simple. Or that complex, whichever your perspective. Now, when we get to electron spin, what we're doing is we're equating the electron is moving on its axis, and it's either spinning this way or that way. So it's -1/2, +1/2. Now, we don't know if it's actually doing that, but it fits the equation and answers the questions. Now, we've got some rules that we have to go by in order to make this thing work. One of those here is the Pauli exclusion principle. We saw Pauli's name before. He came up with this idea. The Pauli exclusion principle simply says that no two electrons in any atom can have the same set of 4 quantum numbers. If they've all got a 3, that both of them have a 3, both of them have a 2, both of them have a 0, then they can't have the same spin. They have to have different spins. Now, they can have any other combination depending on where they're located in the atom, but no two electrons can have the same set of quantum numbers, because that would say they're occupying the same space at the same energy, and they can't do that. Okay, here's the problem with atoms that have more than one electron. We don't know how they're moving. We know their energies because that was our chosen path, but we don't know where they're moving at any one time, right? So if they tend to move close to one another, we know they have a negative charge. If they tend to move close to each other, they're going to have repulsions, right? And if they're at a different distance from the nucleus, they're going to be differently attracted by the positive charges in the nucleus. So we get this convoluted, I don't know what you call it, perturbations to their quantum positions. And because as you add more electrons, the probability of finding them interacting with one another and producing these perturbations is much higher. So that creates a problem for actually making these quantum numbers work. We place them in these levels because that refers to their energies. But as we add more electrons, they tend to modify their neighbors' energies. Let's put it that way. So the calculations that you would do for an energy of an electron in the hydrogen atom would not be the same as one if you have, say, 8 protons in the nucleus and 7 other brothers and sisters out there repelling you. All right, so the electronic structure, we can write it on the board, but in reality, it's an energy, I wouldn't say nightmare, but it's an energy problem for the more complex atoms. And here's what we see. What we're expected to see is for the principal quantum number, this defines the energy. But you'll notice that for 3s, 3p, and 3b, they're slightly different energies. And that's because of the interaction of other orbitals. So we see that the 3d is a little bit higher energy than the 3p and is a little bit higher than the 3s. Okay, here's another concept that is difficult to wrap your head around. I'll admit that. It's called the penetration effect. So I'm going to try to make it really simple. When we say this orbital is at a higher energy than this orbital, this is an averaging effect. So if we say the 3d is at a higher energy level than the 3p, we're saying that the energy of the probability for all the energies that you could find for that electron in the 3d is higher than for the 3p. Now, when we actually look at them, and this is a comparison of 2s and 2p, we actually look at them, the biggest peak for 3s is further from the nucleus than the 3p. But the 3s also has a component that's closer than the 2p. So you see that red line, you get some energy probability there in that big hump, but the little hump is closer to the nucleus. So the averaging effect makes the 2s overall lower energy than the 2p. The penetration is the fact that that small hump is closer to the nucleus. That's the penetration part of the description. That's a simple version. Now we get a little more complex. This one, since it has 2 nodes, is probably a 3. That's a 3s. And the penetration are those small nodes closer to the nucleus. And if we compare all these orbitals from just the 3, notice that the 3s big hump is further away than the 3p and is further away than the 3d in terms of energy. A distance from the nucleus, excuse me, which is energy. But the 3s penetrates deeper than the 3p does, and the 3p penetrates deeper than the 3d. So that's why we can say that the order of energy is 3s is lower, 3p is next, and 3d is higher, because it's an averaging effect. Okay, let's see, we've got till, I could finish the whole thing today, and that would leave Thursday. Leave Thursday, we can talk about the lab. Do like a lab review that's coming up. And I handed out the labs there. If I can get it finished today, and I think I can if I use up all our lab time. We've got till 3:50. Yeah, we should be good. Now we're going to talk about the periodic table. Try to draw correlations here. And as we do that, I'll introduce how to write an electronic configuration for an atom. Well, we're going to get a little bit of history first, because this is the way it happened. It didn't happen by learning just the electronic configuration and then saying, okay, let's do this. Right? This kind of came independently from understanding the structure of the atom. The first chemists that recognized any patterns that were available, that were observed patterns among the different elements, was Johann Dobereiner. And he put together what he called his triads. So these 3 elements in each triad had similar chemical behaviors. And the example that's given there is the halogens, like chlorine, bromine, iodine. That was a triad for him. And these halogens had similar behavior. So you react chlorine with sodium metal, you get a salt, sodium chloride. If you react bromine with sodium, you get a similar type reaction, and you end up with sodium bromide. So those similarities were observed by Dobereiner, but he didn't take it any further than that. So then you come along to 2 different scientists, Julius Lothar Meyer, who's German, and Dmitry Ivanovich Mendeleev. He was obviously Russian. They were investigating in more detail the elements and their relationships to one another. And at this time, there was no understanding as to the structure of the atom. They didn't know that it had protons, neutrons, and electrons. This was before that. So what they were observing was atomic weights as they knew them in those days, and physical and chemical behaviors. Okay. So they arranged these elements according to groups, or I think they called them families back then. We used to call them families, but now the preferred terminology is groups. So the groups in our current periodic table are vertical, and those groups share similar chemical behaviors. So the halogens, the chalcogens, the oxygen group, the pnictogens, the nitrogen groups, they all have similar behaviors in their group. The alkaline metals, the alkaline earths, they have similar behaviors. Okay. And these two researchers arranged those elements in their published tables. What Mendeleev did, though, was he noticed that if he ordered the elements by weight, and as he stepped up in weight, lots of times he would get to the next weight and it would fit perfectly in that group for its behavior, right? But he'd come to some spots and the known element that was next wouldn't fit that behavior. But he said, if I shifted over one more, it's like this group. So he left that spot blank. And he didn't just leave it blank. He actually said, okay, if there's an element in there that hadn't been discovered yet, what might it look like? And he made predictions about its behavior and its mass. And he said, okay, when I publish this table, I'm going to leave this blank and I'm going to say, one of these days, somebody's going to find an element that's going to fit right there. It's going to have these properties. Sure enough, they found it at one time. And that's why Mendeleev gets the lion's share of credit for the periodic table, because he used it to predict the existence of unknown elements. Okay, so this is the layout of the table. See, you've done the extra credit with the table. Okay, so you know a lot of this stuff already, right? Alkaline metals, alkaline earths are the first two columns, and then you get over, and the first two columns and the last six columns are called representative elements. I think the reason they call them that is because they're well behaved for trends in the table. Once you get into the transition elements and the lanthanides and the actinides, they can get a little wonky. But the far right are the noble gases, then the halogens, and the left of them are the chalcogens, and then the nitrogen group, pnictogens, and then you get the carbon group and you get the boron group. And then the lanthanides and the actinides, they fit where lanthanum is and where actinium is. And we pulled those out for two reasons. One is that's so our table won't be a mile long, right, and leave a bunch of blank space. So we just pull them out there and say, this is where they go. And the other reason is the electronic structure of the lanthanides and actinides are very similar. They have their properties because of the position of the electrons in those shells, in the orbitals. So pulling them out makes sense. And then, of course, the transition elements are all in the middle. Now, you've learned also that the non-metals are on the right, the metals on the left, and most of the elements in the table are metals. And then those that are close to that zigzag line, and that zigzag line starts underneath boron and then goes to the right of aluminum and down like that. And on either side of that line are elements that sometimes, depending on the environment, sometimes they behave like metals and sometimes they behave like non-metals. That's why they're called metalloids. And of course, hydrogen's over there all by itself. You can't pigeonhole hydrogen. It's a universe to itself. Okay, we covered the Pauli principle. Now the Aufbau principle, and I'm not sure what Aufbau means. It's German. I don't know what the word means, but the practical meaning is as you build atoms, and you do it one proton at a time, as you go up adding protons to the nucleus, then you add an electron for each one to keep your atoms neutral. Then the electrons go into the next available lowest possible orbit in terms of energy. So you fill them from the low energy and you keep adding up. You don't just skip levels because you want to and you put them out here. You have to do them in order for their ground states. That's the Aufbau principle. So oxygen starts off with, let's see, oxygen is 8 protons. So we start off at the lowest level the principal quantum number 1, and it's that's N, and L would be 0, right? 1 minus L is V0, which is S, right? Then the next highest one, we have to go to 2 because we can't go any higher than that. We go to 2. Now 2 has possibility of S and P. It's a 0 and 1. So it can have an S or it can have a P. And you can keep going if you need it. But I think that's all we need for oxygen. Now, once you get down to this level, then what can you have? You can only have 2 electrons, plus 1/2, minus 1/2. Right? 1 L, M sub L. Well, it doesn't matter here because there's only one possible level. So we put 2 electrons in there, right? One is plus 1/2 and the other is minus 1/2. Sometimes we call it spin up, spin down. It means the same thing. This S can only have 2 in it. So that's 2 electrons. So we've used up 4 of them. Okay. At this level, where we have 1, that M sub L can be minus 1, 0, plus 1. So it can have 3 orbitals in that subshell. Right? Minus 1, 0, plus 1. And each one of those can have 2 electrons in it. Okay. So that brings us, I think, to the next principle, Hund's rule. Hund's rule says that when you have these orbitals in a subshell, you have to put 1 electron in each one until you've got at least 1 in each sub orbital. Then you can go back and start pairing them up. And this allows us to minimize the energy. So we've got what, 4 more? Got 1, 2, 3, 4. That's Hund's rule. Okay. Now your book and the authors, they like to put those boxes with double arrows in them, but I don't. That's too much trouble. I just put a line for the orbital and spin up, spin down. It's a whole lot quicker. But that's the ground state for oxygen. 8 protons, 8 electrons, 2, 4, 8. And you need to put these in order: lowest energy, next highest, and keep going that way. And there's a way to do that. I'll show it to you in a minute. There are 2 ways to do it, actually. I've got a description here, and then you can use the periodic table to do it too, which is sometimes quicker. Okay. The concept of the valence electrons. The valence electrons are the highest energy electrons that have the same principal quantum number. So oxygen has 6 valence electrons. Okay. If we had 3s out here, then we ignore the 2s and go to the 3s. Count those electrons as valence. They're the outermost energy electrons. And the reason we're interested in those is because of the way that we've discovered up to this point of the behavior in chemical reactions of these elements is related to the number and the type of valence electrons. Okay. Now the structure of your periodic table, here it is. We say what orbitals are being filled. The highest orbitals being filled. If you're an alkaline metal or an alkaline earth, the s orbitals are being filled. So let's take an example. Let's say sodium, which has 11. 11 protons, 11 electrons. So we set out our, like that. We know that 8 can handle here. That's not enough. We need another one. So we go to 3s. That's the next one. So we put 2 here, 6 there total, right? 3 orbitals, 2 each is 6. then this can have 2 in it. So 2, 4, 10, that only has 1. And you count those up, that's 11 electrons. Okay, now notice that in the table, you already know this, the table's arranged in groups and periods, periods left to right, groups top to bottom. The period references roughly the principal quantum number. So once we get to 3s, we're at that 3s, the alkaline metals only have 1 electron. Okay. If we went to alkaline earths, like next door neighbor, magnesium has 12. Then these would be the same, and this one would have 2 electrons in it. So what we're saying is, for those first 2 columns, only the s orbitals are being filled. Because once you get past that one, you got to go to a p. And the p orbitals are being filled on the right. All those elements on the right are p orbital fillings, except for hydrogen and helium. Then when you get to the transition metals, all of those orbitals being filled are the d orbitals. And we'll do an example here in a minute. And then when you get to the lanthanides and actinides, those are f orbital fillings. That's the way the periodic table is arranged. S, P, D, F. Now, this is one way to get the energy order of your orbitals correctly done. All right. You set up the s orbitals on the left, 1, 2, 3, 4, 5, 6, 7 s orbitals there. Then the next to them, you have to go to 2 to get your p, so there's no 1p. It's not allowed, right? So you got 2p, and then 3, 4, 5, 6, 7p. And then D is not allowed in 2. So it starts with 3s. So we have 3D, 4, 5, and 6, and then we have Fs, 4 and 5Fs. And you draw your diagonal lines through the 1s, 2s, 2p, 3s. That's as far as we've gone so far. And that's the order of energy. Once you get to 3s, you go back to 3p. So we would put 3p here. And then the next one, 3p is 4s. And then you go back up and put in 3d. So in this case, when you start building atoms that have that many protons and electrons, the energy levels switch. So now the 4s is lower energy than the 3d. The principal quantum number says that this should be higher energy, but in actuality, when you get that many protons and electrons together, the energy switch. So now the 4s is lower energy than the 3d. And then you go 4p, 5s, and then back to 4d. So that's the way, that's the order of energies, right? And I think that's in your useful information if you want to use it. Now, that's one way to do it. The other way to do it is to go to the periodic table. You know which orbitals are being filled, right? So let's go to arsenic. 33 electrons. You know that you're going to have 1s with 2 electrons. 1s, 1 is hydrogen, 1s2 is helium. Then 2s is lithium beryllium. Okay. Then 2p is boron through neon. So that would be neon. Then we go to 3s. Right? Go back down here. This is the third period. That's 3s. So 3s2. That takes you through magnesium. Then you go to 3p, and you got 6 of those. Right here. Then you go to 4s. And you can have 2 of those. That gives you potassium and calcium. Then you go to the transition metals. So when you go from 4s, then you back up to 3d. And 3d is where you pick up scandium. So the d orbitals, they're shifted. This is the fourth period, but the orbital being filled is 3d, not 4. Okay. So 3d has how many to get across all of those? Should be 10 of them, right? Because they're 5 orbitals, 2 electrons each. So that's 3d10. Now, when you get to the other side, you're back to 4. You're back to 4p. And you can see that up there. So how many do you get from 4p? Well, you get 4p1, 2, 3. That's arsenic. So that's how you use the periodic table to fill in. And then once you've done that enough and you're confident with it, you can use a shorthand version if it's allowed. If the question says you can use the shorthand version, you back up to the last time you crossed through the noble gases, which is here, arsenic 18. Right? 2, 4, 10, 18. What's left over? 4s2, 3d10, 4p3. That's the abbreviated version. Okay. This is like a core. Now, what does that tell you? Well, it tells you that for arsenic, you got 4s and 4p. Those are your valence electrons. You got 5 valence electrons. Okay. So if you look at arsenic and its charge possibilities, let's look at our periodic table that has the charges. Here it is. Okay. Arsenic, you have a -3, +3, and a +5. Okay, what does that mean? Well, a +3 would be you would lose those 3. Right? If you lose 3 electrons, you have an excess of 3 protons. So that would be a +3. If you lose these 2, that's a +5. Okay. How would you get a -3? Add 3 more, because P can hold 6. So that explains those charges that you see naturally for these elements. It's easier for the alkali metals and alkaline earths, right? The preferred charge for the alkali metals is +1. They've only got 1 s electron. So you get rid of it, you got a +1. The next door neighbors, you get rid of 2 of those, and you got a +2. Okay, so hopefully it's starting to make sense. Okay. Let's see if we can do these configurations. We can use the periodic table to do it. In fact, that's what I prefer. That keeps me out of trouble. If I have to remember that diagonal thing, I don't have time to draw that out. So I just use the periodic table. The table's always going to be there. So sulfur. How about sulfur? Well, how many electrons does it have? Looks like 16. Okay. So if you haven't memorized, that's fine. Otherwise, you can go 1s2, hydrogen, helium, 2s2, 2p6. That gives us 10. I need 6 more. So 3s2 and 3p4. Looks like. Now, is that right? 3p. 3p. 1, 2, 3, 4. Yep. So that's sulfur. And if we write it in shorthand version, we go from sulfur and we back up to neon. So neon would encompass these guys right here. This would be neon 10. And then you would have these on tacked on the end of it. Barium is a monster. Barium is way down here, 56. Now, it would take us a while to write out barium completely. So what if we go back and say xenon 54? xenon 54. That means we only need 2 more electrons. Well, where do they go? Well, barium is in the 6th period, so it's 6s with, it's in the second one, 2 electrons. So 54 and 2 is 56. Okay, let's see. I think we actually did draw it in. No, we didn't. We abbreviated. I'm not going to do europium. It's let's see, where is it? Here. Oh, we could do a europium, I guess. I haven't typically done it before, but I don't see why we can't. Europium 63. Okay. So where would europium go? It would go right in here, right? So we would back up from there to xenon again. So we go back to xenon as our core. And then where do we go from xenon? Well, we have 6s, 2. And then what is lanthanum? Well, it's 5d. 5d 1, and then you drop down 1 more for the F's. So it'd be 4F, 1, 2, let's see, 1, 2, 3, 4, 5, 6. That's what I would predict. But there are some anomalies in the table. And I'm not sure if that's one of them. Let me see. Yeah. Okay. Here's the thing. When you're talking about low energy and stability, for when you're filling orbitals, if you have something like a D orbital, you have the potential for 5, a D subshell, you have potential for 5 orbitals. All right. So what's the most stable that you can get for that one? Well, all filled or half filled. Half filled is more stable. So for F, you have 7. Right? What's half filled for 7? 7. Right? So instead of putting 4F6, we steal that electron and put it over here. That's lower energy, which satisfies the Aufbau principle. That's what we call an anomaly. It's not what you expect, but there is an explanation for it. And you see those also in the transition metals, right? If you come along here and you go 3D 1, 2, 3, 4, 5, that's fine. 3D 5 is very stable. But if you get to actually, when you get 1, 2, 3, when you get to 4, you've got the 4 S's, and you're going to take one of those S's and put it in here and make that 5. It's more stable. And when you get out to here, you've got 9. It'd be more stable with 10. So you take one of these S's and put it in there and make that 10. Those are anomalies also. We'll probably talk about those again later. Okay. So right now, your head's probably spinning. But the electronic configurations are very logical. They follow a pattern that's easy to learn. And you just need practice. Now, as far as periodic trends go, what we mean by that is in the periodic table, we can compare these various descriptive energies or whatever else, measurements, these descriptive measurements follow a trend in the table. So as you go from one place to another, as you move through the elements, you see a trend in ionization energy, electron affinity, atomic radius. Now we're going to take these one at a time. And first we have to define, what do we mean by ionization energy? Well, we're going to use our generic, right? Whatever the symbol is, whatever the element is, doesn't matter, is neutral. And we're going to put it in a gaseous state. Now, if we're looking to find the energy of ionization, we want it in the gaseous state, because if it's a liquid or a solid, some of the energy that you put in there is going to be phase change only. It won't have anything to do with the electrons. So we want to get it in the gaseous state so that the energy that we follow and put in goes all into ionizing, removing that electron. So the gaseous state of our element then produces a singly charged gaseous ion plus a free electron. Okay, the energy required to do that is called the first ionization energy. And it's usually in kilojoules per mole. And then if you want to go further, if you want to take out another electron, you do the second ionization energy, and it's still a gas. So you add more energy, and now you get a 2+ charge with 1 electron. And you can keep doing that. Just remove 1 electron at a time, and you get values. Notice that for magnesium, it takes a certain amount of energy to remove that first electron, right? But the second electron is a little more difficult. And it's really a simple explanation. When you try to remove a negative charge from an already positive charged species, it takes more energy because there's electrostatic attraction. So the second one takes twice as much energy. Okay. Now, why when we go to the third one does it take 10 times as much as the first one? Now you're getting into the core, right? Remember, magnesium is, let's see, 12. So it's 1s2, 2s2, 2p6, 3s2, it's 12. So the first 2 came out of this valence shell, okay? But the third one comes out of this core. And that takes a huge amount of energy. Anytime you start taking electrons out of the core, you're going to see the energy jump. That's the definition of ionization energy. Okay. So what's the trend? Well, the trend in the periodic table for ionization energies, and for now, we're going to stick to first ionization energies. But you can draw conclusions about second, and third, and fourth ionization energies if you want. But since we're limited in time, first ionization energies is where we're going to stop for this trend. Now, what we see in the table is that for the first ionization energy, the value increases from left to right. So if I draw a periodic table here like this is Y, and this goes over here like that, like that. First ionization energy from left to right, and it works best if you don't have to go through the D's, right? So if we stay up here in the second and third period, then the first ionization energy increases from left to right. Ionization energy number 1. The reason for that is that you're still in the second period and your electrons are in this subshell, but you're adding more nuclear charge. And that is a stronger attraction for the electrons in that level. Okay, so that explains the increase from left to right. The ionization energy, that's for periods. In groups, the ionization energy increases this direction. That was a little more difficult to understand. You increase ionization energy based upon what's the strength of attraction for the electrons. So what you get here is you're going through different levels. Energy levels out here are very far from the nucleus. Right? They've already got a lot of energy and just needs a little bit more to get them off. And then as you move up here, actually at these higher levels, you've got electrons closer to the nucleus producing what's called a shielding effect. So their negativity is balancing the positivity from the nucleus, and the outer electrons don't feel it. Okay, that shielding effect. So as you get smaller and smaller, electrons get closer to the nucleus, there's not as much shielding. So it takes more and more energy to get them off. So the trend in the period is increase left to right, increase bottom to top. So if we put these two together, the increase is lower left, upper right. Okay. And there's the black and white explanation that I just gave. Okay. So the first ionization energies here are shown for elements in order, right? The atomic numbers on the x-axis, and as you go across, you get increased atomic number, and you'll see the trends from the lower ionization energy for radon, and then xenon and krypton. So if we stay in that group, the noble gases, we see that the ionization energy goes up as we get closer and smaller toward helium. And you can see that trend in the rest of them. Now, there are anomalies, okay? And they're related to the electronic structure of the elements. So what we see here is the first anomaly we see is lithium, boron, beryllium, carbon. Lithium, beryllium, boron, carbon. So when you jump from beryllium to boron, you're moving from S to P. So if you go up to beryllium, you've gone from left to right. Lithium to beryllium, you get an increase because of the increased nuclear charge. But when you go to when you jump to boron from beryllium, you're moving from S to P, and P is further out in energy and distance. So the energy drops for boron before it starts going up again. And then it increases from boron, carbon, to nitrogen. Okay, so what do we have at nitrogen? We have 2p. For nitrogen, we have 2p3. So that's 1, 2, 3. There. Very stable, right? Half filled, one in each. But when you go to oxygen, you've got that orbital with like that. Okay. And notice that oxygen there, the energy drops. First ionization energy drops. That's because this electron is feeling a repulsion from that electron. And it's already got some energy of repulsion, so it just takes a little bit more to get it loose. So oxygen, first ionization energy, drops. Okay. Then you start going back up toward fluorine and neon. So you see similar anomalies, not as pronounced as nitrogen, oxygen, but phosphorus and sulfur do the same thing. And then you get into the wigglies there next to zinc. Now you're down into the transition metals, and they're kind of wonky. But as long as we stay in the S's and P's, the trends are very predictable. Explain why the graph of ionization energy versus atomic number is not linear. Primarily electron repulsions. And we showed that here. And these are where some of the exceptions are between beryllium, boron, nitrogen, and oxygen, and there's some others. Okay, so let's use what we know to predict. Which atom will require more energy to remove an electron, sodium or chlorine? Well, sodium's on the far, they're in the same period. Sodium's far left, chlorine's far right. So the trend says that chlorine's going to take more energy because of the increased nuclear charge. So let's see if that's here. Yeah, chlorine. Well, it says why, but it leaves it to the instructor to explain. How about lithium and cesium? Well, now we're in the alkali metals, and lithium versus cesium at the bottom. Cesium should be the lowest, so lithium will be the highest. How about, for a moment, let's look at second ionization energy. Which one is largest? Lithium and beryllium. Lithium has a 1s2, 2s1. Right? Only 3. Beryllium has 4. So it's going to be a 1s2, 2s2. Okay, first ionization energy removes that electron. Right, that one's gone. This one becomes 1. Now we've got singly charged. Second ionization energy. Where is the electron coming from? Here it's still coming from the valence. Right? So it's going to jump up, but it's not going to jump up like this one because now we're taking electrons from the core. So lithium should have the highest second ionization energy. The core effect. And this whole table shows you the core effect for a series of elements, sodium through argon. And you see that there's incremental increases from left to right as you go through the first, second, third, fourth ionization energies. But when you get to the core in any one of these, it jumps way up for each one. The more electrons you have in the valence shells, the more you have to remove before you get to the core. All right, that was ionization energy. Now let's look at electron affinity. Let's see, let's remove this. Here. What do we mean by electron affinity? Again, we start with the gas. But instead of removing electron, we want to know how much energy do we get back when it picks up an electron, right? Because an electron from infinity being attracted to the atom is going to give up energy. Okay? So we add an electron, which makes a negative gaseous ion, and we get energy back. Now, when that happens, we use the same sign convention as we did for calorimetry, right? If it's negative, the energy is leaving the system. This is the system. So when the electron drops into this atom, it gives up energy, which means it's a negative value. So the higher the negative value, the stronger the electron affinity. So the more negative is a higher affinity. Okay, I want to make that clear. So what's the trend? Well, in general, as we go through a period from left to right, the electron affinities become more negative, which means the attraction is stronger. So electron affinities from left to right, more negative, which means stronger attraction. Okay. And in a group, the electron affinities become more positive as you go down. So if we're going more negative, then it would be the other direction. The electron affinities increase negatively this way, more negative. And there's a similar logic to ionization energy as to why this is. I don't have a slide on it, but as you increase the effective nuclear charge from left to right, they have a stronger attraction toward the electrons. And as they come from infinity to a lower energy level as you move up, then that gives off more energy too. I mean, they're not coming down to a 4p orbital for a big atom. They're coming down maybe to a 2s orbital. And that's a bigger jump. So you give up more energy. Okay. The next trend that we're going to talk about in this chapter, oops, I didn't mean to do that. I have to redraw it, is atomic radius. Okay, let's see, this second and third period. Atomic radius. The problem with atomic radius is, how do you measure it? Well, it depends. If the element is a metal, you do it one way. If it's a non-metal, you might do it another way. If you're looking at, well, we won't look at ionic compounds because that's not atomic radius, that's ionic radius. So that's another topic. But if you can determine the distance between the nuclei in a, say, a chemical bond, or in a metal lattice, right? And we can do that fairly accurately with electron diffraction. Then you can take half of that value, and that's your atomic radius. So that's all that this is saying. And the values will vary. It depends on the researcher. Okay. This is for the metals, and X-ray diffraction is a very good technique for determining that distance. Covalent radius is the half of the distance between the nuclei in a homonuclear diatomic molecule. So you would take something like hydrogen, right? Or nitrogen, or let's see, fluorine. These would probably be better than this one. That triple bond is not going to be good. So if you have this one, chlorine, right, where you have single bonds, then you're more likely to get a closer approximation of the atomic radius. Now, the covalent radius is not, strictly speaking, the atomic radius, because we know that there has to be some orbital overlap to get those nuclei close together. So the covalent radius is probably going to be smaller than the true atomic radius. But if we're comparing apples and apples, then we're looking for trends, then it might work. And there are several ways you can do that. X-ray diffraction, electron spectroscopy, neutron diffraction, microwave spectroscopy, and other elements, other methods. So what's the trend? Well, from left to right, the atomic radius tends to decrease. And for a similar reason to the ionization energy, you're increasing the effective nuclear charge. And what that does is, with a stronger nucleus, it pulls all the electrons closer to it. And that shrinks the size of the atom. Now, the atomic radius for a group tends to go get bigger as you go down. So increase this way, atomic radius. Increase from left to right. Atomic radius here from top to bottom. And that's primarily due to the fact that as you go down, you're adding electrons to the next principal quantum number, the next level out. So they're getting bigger and bigger and bigger. So it gets bigger this way, and it gets bigger this way. So the trend for atomic radius is just the opposite of ionization energy. Upper left, lower right is the increase in atomic radius. Now, if we look at just the representative elements, like the first two columns and the last six, we get a fairly consistent trend. Right? If you go into the transition elements, they'll do like this and like this. So they don't stick to the trend as religiously as the representative elements. So which one should be larger, sodium or chlorine? Well, sodium's over there, chlorine's over here. Chlorine should be smaller. Atomic, neutral atom. Right, that should be smaller. Oh, wait a minute. Larger, I'm sorry, larger, not smaller. Sodium's larger. Now, when you get to the ions, it flips. When you add an electron to chlorine, you're making it bigger. When you take an electron from sodium, you're taking an electron from an entire principal quantum level. Now that shrinks it way down. So the ion reverses. Sodium plus is much smaller than chlorine minus. How about this one? Which is larger? Well, I would expect cesium to be the largest because it's a higher quantum level. Okay, this is going to be a little bit trickier. Which is larger, the hydrogen 1s orbital or the lithium 1s orbital? Now, we're just talking about those specific orbitals. So hydrogen 1s, that's it. Lithium is 3. It's 1s. Well, it has, actually it's 1s2, 2s1, like that. Okay, when we're looking at individual orbitals, it's best to consider what's the nuclear charge. So this orbital is it's the closest to the nucleus in either one. But this one has 1 positive charge, this one has 3 positive charge, and this one is really close to the nucleus. So it's going to feel that positive charge with nothing in between. So this orbital should be a lot smaller than that orbital. Well, and larger, 1s should be larger. Yeah. How about lowest energy? Well, the smallest one's going to be in the lowest energy. Lithium's going to have the lowest energy, 1s orbital, because it's closer to the nucleus. Okay. Let's see if we can put these in order. Arrange these elements: oxygen, fluorine, sulfur. So let's see, oxygen is right here, fluorine's there, and that's neon. And then below oxygen is sulfur in the third period. Oxygen's in the second. Okay. So let's put them in order in ionization energy. Lower left to upper right. So it should be, is it increasing ionization energy? So it should be sulfur is less than oxygen is less than fluorine. Ionization energy. First ionization energy. Okay, atomic size should go just the opposite. Right? Instead of lower left, upper right, it's upper right to lower left. So atomic size should be fluorine, and then oxygen is larger and sulfur is larger. Okay. Okay. Let's see. Final thoughts. The number and type of valence electrons that primarily determine an atom's chemistry. Those are the electrons that other atoms see when they approach. And that's where the interaction occurs. Those valence electrons. That's what determines the chemistry. And that's why Mendeleev and Meyer saw, and Doberreiner, all three of them saw those relationships because they were in the same family. They had the same number of valence electrons. They're at different energies, of course, but they were still, those electrons were available for reaction. Electron configurations can be determined from the organization of the periodic table. Yep, we did that. Certain groups in the periodic table have special names. That's nothing new. Basic division of the elements in the periodic table, metals and nonmetals. All right. I guess that's final thoughts. Can't go any better than that in the time allotted. Okay, so we'll come back on Thursday. And well, let me check the schedule. Let's look at the schedule. We've introduced this material. That's good. No lab today. Yeah, I got a buffer built in. So what we can do on Thursday is run through the lab and get a feel for the lab. And that'll give you a chance to set up your notebook more efficiently during that buffer day on Thursday. And then April 1st, that should give you enough time by next Tuesday to have worked enough of these problems where you have questions or the review session would make more sense. So rather than do the review right 2 days from now, which probably wouldn't help you much, we'll look at the lab instead. Okay, let's see, we can stop the share and we're done for the day, folks.